Good morning. Good morning, everyone, and welcome to the third annual Multi-Cloud Conference. This year, we are focusing on Zero Trust architecture and DevSecOps for cloud-native applications. Please note, this event is recorded. We are starting day one of the event with an interactive training with Envoy and Istio. It's going to be fantastic, so please hang around your computers and be ready to absorb all the important information that the presenters are going to offer. Before we go there, I have some announcements. So please join us in our work on multi-cloud public working group. And you'll have to basically subscribe for that working group to join our effort. Is you have a QR bar there that will take you to receive all the information that is necessary, and that will allow you to subscribe to our mailing list. Also, please note that you are going to learn tomorrow about open security controls assessment language, and we have a third annual workshop on March 1st and 2nd. Again, you have a QR bar that will allow you to find more information. And today's event training is recorded. But in any case, if you would like to have another training in person, and by watching the recorded session will not be sufficient for you, Tetrate team was very kind and promised that they're going to do a retake. A date will be announced, and they will provide additional information by working with you all. So coming back to today's business, Tetrate team is welcoming you to a Platform One deployment, showcasing the use of Istio, Kubernetes, and other tools to build in-app and user-level security permissions, encryption in transit, enhance identity and access control, and to provide runtime observability required to achieve a zero-trust platform in practice. Today's speakers are Zach Butcher and Adam Zicki. Zach is a founding engineer at Tetrate and has helped in a variety of roles across the company. Currently, he is the head of product. At Tetrate, he works with some of the larger enterprises in the world to adopt Envoy and Istio. Adam is an engineer lead at Tetrate, and he focuses on, and did that for nearly the past decade, on helping global 2000 companies modernize their infrastructure platform and adopt cloud-native application architectures. Enjoy the training and learn what should come first, Kubernetes or Istio. Zach, please take it.
Yep, thanks, Michaela. Welcome, everybody. We're super glad to have you. Adam and I are excited about today. So just before we dive in, a little bit of housekeeping here. This is interactive. Unfortunately, it's not quite as interactive as we had wanted it to be. So I know that there was a question or two around like bringing Kubernetes cluster or similar. Unfortunately, you won't be able to follow one with us hands-on today. And we had to make that change in the interest of having more attendees. We would only be able to have about 1/10 of the people that are in the call right now if we were doing hands-on. The follow-on sessions that we are doing that are going to be available that Michaela mentioned are going to be hands-on. So I apologize. Today, we're going to be kind of giving you a little bit of a guided tour, and we're going to be talking about a lot of the background and theory and how it applies in practice. And we're going to be showing you all that in the real environment. And throughout that, we would please, ask you all to ask questions. We're going to be answering those in line throughout. I'll be monitoring those very closely. Some of those we'll answer in text. Some of them we'll address directly, verbally in the call. So please get your questions in as we're going through, and we'll do our best to answer everything there. Like Michaela said, this is recorded, so you'll have this for reference to be able to go back to as well. And please make sure, if you have questions, if you have concerns, if there's something that's going on, drop a note in the moderator chat, send us an email at conference@nist.gov. conferences at NIST.gov, and we'll do our best to jump on it immediately. With that, let's go ahead and get started. So a little bit of a taste of what we're going to be diving through today. We're going to give you a little bit of an intro here. We're going to give a little bit of background on the service mesh itself, some of the basic pieces and the capabilities that it brings. Then we're going to talk about really how we start to assemble that ZTA platform. And you'll have to excuse me, y'all. I've been a little bit sick this past week. I had a 102-degree fever last night. Feeling much better today, but I'm a little bit congested. So if you hear me clearing my throat or somewhere, I hope you'll excuse me. We'll give a little bit of that service mesh intro, and then we'll get into what it really takes to make a zero trust platform, right? We'll talk about some of the multi-tenancy. We'll talk about how we start to extend this beyond, maybe a single Kubernetes cluster or a single, data center, and how we start to weave a coherent mesh and have a coherent infrastructure wherever we're running across on-prem, multiple clouds, whatever it is that we need in our site, in our organization, and how we can have consistent security there across it. And even, and this is something we're particularly excited to talk about, how we can start to bring the service mesh back into legacy environments as well, right? This is a key thing for us that we believe very firmly, is that the ideas that the service mesh brings, that we're going to talk about at length today and into tomorrow, are not just for new and modern applications that are deployed in Kubernetes, but they're really for all of our applications. And we're going to spend a decent little bit of time today talking about how we can kind of bridge the gap between legacy and modern infrastructure, how we can bring legacy workloads like VMs into the service mesh and have a lot of the security controls there. Then we'll get into the observability and troubleshooting side of it, right? If we're going to build a bunch of controls into this runtime system and we're going to be deploying our apps onto them, we need to be able to understand that system, how it's behaving, how it's working, that our controls are actually being enforced. And from an operations perspective for our application developers, giving them the tools they need to actually, work and run the application, right? Be able to troubleshoot it in production. Finally, we're going to kind of wrap it up by tying back all the kind of different stuff that we've talked about into the umbrella of ZTA, right? So throughout, we're going to be talking about some of the security side, and hopefully you'll see how basically everything we're talking about today has some kind of piece to play in the zero trust story. But we're going to close out this workshop by directly addressing that and trying to put a little bit of a neater bow on it. And that'll also be a little bit of a preview of some of the stuff we're talking about tomorrow. And then finally, we'll have a dedicated kind of Q&A session at the end for anything that we didn't get wrapped up or anything that we didn't get answered neatly. Alrighty, so with that, we're going to go ahead and dive in. So just a real quick intro about us. Michaela, I think, did an excellent job, but the folks at Tetrate have been collaborating with NIST in a bunch of different ways. And additionally, we're very heavily involved in the open source communities that back a bunch of the technologies that we're going to be kind of showing today. In particular, I work very heavily on the Istio project. I'm one of the community elected steering committee members. I wrote the book Istio Up and Running. I also work very closely with the folks over at NIST to help author some of the special publications that govern microservice security. In particular, I work on the SB 800-204 series. Adam, if you would like to give just a little bit about yourself here.
Yeah, absolutely. Yeah, no, I think Michaela gave a great introduction. I work alongside Zach and the other folks here at Tetrate. Long history in Kubernetes, containers, modern applications. Been doing that for nearly a decade. So I think that's fine for now.
Yeah. And again, just to touch on some of the stuff we do with NIST, we interact with them in kind of three primary prongs. This slide is a little bit out of date, as obviously that Jan 2022 is not upcoming, it is happening. Right now, you're in it. But we do a lot of research in access control. When we talk about the multi-tenancy in the system, this is really where access control is going to come into play, and we'll discuss some of that. We'll also talk about this at length tomorrow, and that's going to be the subject of my talk tomorrow. That's about SB 800-204B, as well as a couple of the other talks. Otherwise, we collaborate again on those SP 800-204 series of papers that are really all about is microservice security. What is it that we do? We think that because of the challenges that ZTA, that our modern cloud environments are introducing, that we really need to go back and kind of think about how we connect our applications. And so we call this an application-aware networking platform. And we build it based on Istio and Envoy. And you'll see this on top of Platform One in just a second. We'll talk about what Platform One is and everything as well, right? But the key thing that we want this platform to enable is central governance, right? We want to be able to set out directives for our organization around runtime security, towards the goal of realizing ZTA, right? However, the controls that we actually need to implement across our company, across our organization, are going to be different for different parts of the business, right? Different divisions, different business units are typically going to need or have different constraints. Therefore, the controls that they might need are going to be different, even though they still realize that governance that the central team, that the central organization needs, right? And the net result of being able to collaborate to build the right controls for each part of the business should be that local developers are enabled to build their application and deliver value to customers more quickly, more safely and securely, because there's a lot of security baked into the platform. And we'll talk about how this gets realized. So what are we actually going to be showing today? We're going to be showing a whole bunch of different clusters, and we'll break down a much more detailed view. But we're going to be showing a whole bunch of different clusters that are around, and they're going to be linked together with a management plane that's providing some of the tenancy availability, some of the security and access control, and some of the lifecycle management. And so this is what we're going to be spending a lot of today talking about. But to get started with that, I first want to talk about the baseline kind of platform, the compute that we're going to be running on. So hopefully it's not new to most of the folks in this call. The Platform One, and I apologize, I'm going back and reading some of the questions that are coming into chat. The PowerPoint will be shared with everybody after this. Yes, the attendees list is hidden by design. Platform One is a project out of the Air Force that is geared towards building a platform for realizing zero trust, and the goal is that it's reusable, right? The platform itself is composed of a few key value streams. There's 4 primary value streams in it. The first is Iron Bank, which is vetted, scanned, and approved container images for a whole bunch of different systems that you can go take and use, right? And you can use these in your site, and you'll get the benefits of the security scanning, the additional patching, all the stuff that goes into having these prepared images. Second is Big Bang, which is the actual instantiation of Kubernetes and a whole bunch of other auxiliary software using those Iron Bank containers. To have a platform that you can run mission applications on top of safely and securely. And that software stack is going to run on cloud provider infrastructure or your own on-prem infrastructure, right? And that stack has, again, a whole bunch of different parts, but it includes Kubernetes. It includes Istio, the service mesh that we're going to be talking about today. It includes facilities for doing SSO. It includes, of course, encryption and transit and a whole bunch of other things that we'll talk about at length. The third value stream is CNAPP, the Cloud Native Access Point, which is really all about pushing identity and access down to devices, right? So it's really trying to close out the user identity side of zero trust as they're coming into the system, right? And then finally, they have a shared environment party bus, which is really around the support and community that the Platform One team has built as they're getting users, as they're having different federal agencies, different programs adopt it. That's how they provide support for the software. And that's how, so the customers come in and help support each other, right? So Platform One in general is a really, really cool stack. And what we're going to be showing is how we can start to stitch together several of these and into a coherent whole. Somebody asked, when did Big Bang start including Kubernetes? Big Bang does not necessarily include the Kubernetes distro. You can pick the distro that you use with Big Bang. Big Bang is instantiated on top of that. However, Big Bang is, kind of inherently tied to Kubernetes, so I kind of consider that part of it. Certainly, we can dig into it a little bit more, but the important thing to think about is Big Bang is this runtime platform that incorporates Kubernetes, incorporates Istio, and a couple other runtime components besides. But by design for Big Bang, you can bring your own Kubernetes, right? The goal is to be able to let teams, for example, run K3s when they're on-prem or in restricted, have small compute environments, be able to use a cloud provider hosted Kubernetes when they're in a cloud environment, right? So the goal is to facilitate people being able to consume the best in breed. And let me ask my moderator team, I see a couple questions around people having issues during the presentation. Is it looking good for y'all? Tell me in chat. Okay, so this is a real quick intro to Platform One itself. We're going to touch on it a little bit more throughout the demo as we're weaving together some Big Bang clusters together with some OpenShift, some EKS, and some other clusters into a single coherent mesh. But before we get into that, why don't we talk about what the service mesh is itself? So I think one of the most useful ways to get in and understand the service mesh and really anything is to understand the problem statement that it's trying to solve, right? And so if I try and sum this up concisely, this is the problem statement, right? We're undergoing a large-scale architectural shift in our industry. We need to pursue this shift to allow for agility, to allow for our developers to move more quickly, but it is introducing new problems. And in particular, the adoption of a microservice-oriented architecture in modern, highly dynamic environments leaves us unable with traditional tools to effectively monitor, connect, manage, and secure our applications and their communication. And we see this with traditional perimeter-based security models falling down, right, and not being able to work effectively. We see this in the challenge in bringing modern cloud infrastructure together with our legacy on-prem perimeter-based infrastructure. And it's really hard to unify the two security models and not have gaps that leave us insecure. I want to touch in though on what do I mean by a modern distributed architecture? There's a couple different pieces. So one, it tends to be container-based, right? That's maybe a little bit less important than the second and third, which are the environments are highly dynamic that we're deploying into, right? A VM in a traditional infrastructure might, for example, live for a year or more. A pod in Kubernetes might live for a day, right? Maybe longer, but there's really no guarantee, right? Similarly, we're not going to have a dedicated IP address for this workload in general, right? That's persistent that I can put into a firewall rule. That's just not how a lot of the cloud environments like ECS or Fargate or EKS, just to name some of the AWS ones, but there's similar equivalents across the cloud providers. That's not really how they work. It's highly dynamic, right? And maybe most importantly of all, our applications are composed over the network, right? And where previously we had procedure calls in our monolith, we now have remote procedure calls, RPCs, that go over the network. And this introduces a ton of complexity, right? So how do we start to address this, right? Or what are some of the problems in each of those four areas that I called out, right? So first off, for monitoring, we need to understand what's actually going on. We have kind of three pillars that start this, which are metrics, logs, and tracing. And those are great baseline tools for beginning to understand our runtime system. The question is, how do we do, for example, metrics, logging, and tracing consistently across our entire fleet? There's a lot of value in, for example, having the same log line format for every service, because then I can start to build consistent pipelines for processing logs that then any system, any application in my system can come in and plug into and get benefits for free. Same, for example, for metrics. By having a consistent set of metrics with the same dimensions, with the same semantics on those dimensions of those metrics, I can start to build automatic dashboards that my teams get out of the box when they come onto the platform. All of these things help accelerate the time to value, right? They help reduce the amount of work that an application team needs to do because you can provide it out of the box in the platform. We need to connect our applications, right? I mentioned, maybe the biggest problem is that the network is an inherent part of our application, and there's a lot of stuff that goes along with that, like service discovery. How do I actually figure out who I need to talk to and where that job is deployed? Resiliency. In the face of transient network failures, how do I actually keep my application reliable, right? How do I route around a failure? How do I implement retries? How do I do that in a way that's safe and isn't going to introduce other kinds of cascading failures in my system? And then finally, given service discovery and a bunch of this resiliency stuff going on, how do I actually load balance all this, right? How do I distribute the traffic across everybody that's across everything I'm trying to communicate with? And ideally, we would like to be able to do that client side and not have this like center reverse proxy at every step of our infrastructure, right? Because A, that introduces a failure point, especially if those proxies are shared. B, they're just not needed anymore. And we'll talk about why they're not needed. Finally, we want to manage our traffic, right? We want to control what things flow where, how. And when I say control, I don't just mean what connections exist in the system, but I also mean actually doing this at a request level, right? So it's not just when you establish a connection, I'm going to apply some policy, and then whatever goes over that connection is just good to go. That's not actually an acceptable stance when it comes to zero trust. And well, depending on your protocol, we can get into the depth, but certainly when we're talking about things like HTTP, for example, that's not good enough, right? For some protocols that are connection oriented, that are TCP oriented, like SQL, it may be good enough, right? But certainly when we're doing request oriented protocols that we can understand at L7, like HTTP, like gRPC, Thrift, all of these different RPC frameworks, we should be able to operate on them per request. And that way we can do authentication and authorization per request. We can do traffic and load balancing per request. We can apply policy at that level, right? And when I say policy, I don't just mean security policy, like authentication and authorization. I also mean traffic policy, like rate limiting, like load balancing or canarying. One of the things that we'll show you off today, for example, is being able to implement the strangler pattern, migrating traffic from VMs into a modern Kubernetes environment. And we can do that by selecting very specific subsets of traffic to send over, not just 1% of all traffic, or not just half, but specific users we can target and migrate over, right? So fine-grained policy, not just at the connection level, but at the request level, not just for security, but for traffic management as well. And then finally, we want to get security out of the network, right? This legacy idea of a perimeter-based security model, and then once you're past the perimeter, access is authorization, does not fly. In fact, actually, there was an OMB memorandum today that came out earlier this morning that I thought really nicely summed up this zero trust idea. And it went ahead and said, assume everything is exposed to the internet. Right? Assume that all of your applications are on the internet. That's the security model that you need to be working in from now on. That's spot on, right? And so when everything is exposed to the internet, there's no such thing as a privileged network connection or a privileged location on the network to access the service. So I can't trust the fact that you're on my local network to allow you access. Instead, I need something else to base that access on. The service mesh gives us ways to assign an identity to an application, to a workload, an L7 identity, right? Not just where it lives on the network, but what application it is. we can then start to write policy based on that identity, not based on network location. And so we have policy then that translates, or that is movable, right? If I take my system and I deploy it in cloud, or if I take my system and deploy it in on-prem, that my security policies are going to be the same, because they're not tied to a location on network, they're tied to an application's identity. And so as long as we have that application identity and that's going everywhere, then our policies are going to work. And then finally, all of those things in those 4 buckets that I just described are not new, right? We've been doing them for years. And there's been a whole bunch of different ways that we've achieved it, whether that's frameworks in our applications like Hystrix, whether that's that SDKs that are included in libraries and similar. There's a bunch of different ways to facilitate that functionality. So the key thing that the service mesh is starting to do is bring that consistently across the fleet, give you centralized control over it, one place to go and change. And then finally, make it easy to change. Do it with configuration driven, not embedded in code that requires redeploys. Right. So again, if we were going to bring this all into one slide, the service mesh brings a bunch of good stuff here, like service discovery, resiliency, load balancing, traffic policy, policy per request, identity, authorization, metrics, logs, and tracing. But critically, it does it consistently across the fleet with centralized control, with configuration-based, with a configuration-based model. So it's easy to use as code. It's easy to change quickly. So that's great. We've talked about the service mesh in general. Today, we're going to be talking about a specific concrete implementation of the service mesh Istio. This is the default service mesh that ships in Platform 1 as part of the Big Bang deployment. And it's the service mesh that we've worked on here at TouchRate, that I personally helped create back at Google before then. And so Istio is specifically, it is exactly a system built to address these 4 concerns, right? Which is monitoring, securing, connecting, and managing traffic. So how do we do that? Let's go and assume we have a very simple setup. We have 2 services, A and B, that want to communicate with each other. They're going to communicate over the network, right? Let's assume that it's HTTP traffic. It doesn't have to be, right? It can be any network-oriented communication, but certainly for ease of our understanding and for being able to do L7 stuff, let's assume it's HTTP. So the first thing that we do to realize those features is deploy an Envoy, a sidecar, what we call a sidecar proxy, next to the application. The particular sidecar that we picked is called Envoy. It's a CNCF project. It was one of the first projects to graduate the CNCF. It's very widely deployed and used. It was first developed by Lyft there, but it's since seen really, really heavy adoption across industry, including, for example, Google building out some of their new load balancing products using Envoy. Other cloud providers are starting to build products based on Envoy. We've seen kind of major infrastructure companies start to invest heavily in it. It's really becoming ubiquitously used because it's very lightweight, it's highly dynamic and configurable, and it's pretty performant. We see, this is a bunch of different functionality to be able to inject, and Envoy is the key piece that lets us implement all this functionality. And it only typically takes about, maybe 2.5 milliseconds at the P90, at the 90th percentile to give us this functionality. So that's typically a pretty decent trade-off for that stuff. So we put that Envoy there, and we make that Envoy intercept all traffic into and out of the set of applications. That's great. I mentioned that Envoy is very highly dynamic. So the other half that we need then is a system that's going to program those envoys, right? That's going to stitch them together to give them a coherent set of configurations and coherent behavior. And we call that the control plane. And this is really what Istio brings. And so this is packaged up into one deployment called Istio-D, but there's a couple of different kind of logical pieces that go on here. Part of the reason we're telling about these is that if you go and look at the code, if you want to get involved, you're going to still see these logical pieces, even though there's only one deployed binary Istio-D, which we'll show you in a little bit. The first piece is Galley. This is responsible for sucking up configuration in the system, validating it, and then handing it to the other pieces of the system. The second, and maybe kind of the heart of Istio-D is what's called the pilot component. Pilot is responsible for sending configuration to envoys at runtime. So it translates from that Istio configuration that you write that's intended to be, a little bit easier for humans to consume, and produces envoy configuration that's a little bit lower level that programs a specific envoy instance that's deployed to implement kind of the mesh behavior overall. And by the way, it's not just when I talk about configuration, that's not just like networking traffic configuration. That includes also security policy that we want to push down, that we want Envoy to enforce. And Envoy can enforce a pretty wide range of policy today, including things like JOT authentication and authorization based on JOT claims. Certainly, things like a spiffy identity for runtime service identity. We'll talk about all that at length in the security section. But there's a lot of different policy that we can start to do in Envoy, including, again, not just security, but traffic-oriented policy like rate limiting. And then finally, we have a component called Citadel, which is the certificate authority that's part of Istio-D that's responsible for issuing identity certificates to every part of the system. We use a specification called SPIFFY, the Secure Production Identity Framework for Everyone, to encode identities into a certificate. Those certificates are given to envoys at runtime, and envoys use those certificates when they communicate with each other to A, establish mutual TLS so that we have encryption in transit, but B, we do it mutually so that both the client and the server have the identities that are encoded in those certificates. So both of them can then authenticate that identity and make an access control decision, an authorization decision based on that. One of the questions in chat is, how is Envoy deployed? Is it once per service? Is it once per? We deploy one instance of Envoy next to every single instance of the application. So one instance of the application gets one instance of Envoy. And that's why we call it a sidecar deployment model. The two go together. And this is really, really important. And the primary reason we do this is because of the identity. We don't want a confused deputy. We don't want one proxy holding a bunch of different identities. We want to keep it simple. So we rely on the underlying operating system, the underlying system's primitives to keep isolation. So your application is a container. We deploy Envoy in that container. If we're going to a VM, we deploy Envoy on the same VM as the application. There's going to be many, many instances of Envoy running. All traffic into and out of that application will go through its dedicated Envoy instance for all of that policy. Another question is, hey, what about like non-connection oriented protocols? Can we do UDP? Can we do other ones? And the answer is that's a work in progress today. And so there is preliminary UDP support in Envoy that's primarily been built out to support Quick 3 in HTTP 3 when that comes down the line. However, there's also been interest in SMTP support from the telco space and others. So other protocols and other connection systems, other than TCP are in work, right? Another question is, how long does it take Pilot to push this policy? And the answer is that the system is eventually consistent, but typically it only takes maybe a second or so. A handful of seconds in a very large system for us to push policy. So it's very, very dynamic. And then, there's some other questions around how do we do things outside of the mesh? How do we do encryption in transit? We're going to get into that in a little bit in the demo. And then again, let me just remind folks that, I'm sorry, I'm going through questions here. Let me just remind folks that unfortunately, to be able to facilitate all the attendees today, we weren't able to do it this session interactive. There will be follow-on sessions that will be interactive and hands-on for y'all. Today is going to be primarily a guided tour. Okay. So now let's break down the service mesh and let's see how this actually works. So we go back, we have Envoy deployed next to our two applications. A wants to call B. The first thing that happens is, like I said, Envoy intercepts that traffic from A. There's a whole bunch of different ways to set this up, this traffic interception. By default in Kubernetes, we do this by rewriting IP tables. And so we tell the kernel to send all traffic into and out of that C group or that network namespace through Envoy, right? There's other ways that we can do this. For example, you could have your application communicate over the loopback address and have Envoy take the traffic from loopback and forward it correctly. You could also, for example, communicate over a domain socket. So there's many different ways that we can facilitate this, but either way, whichever way we decide, Envoy is going to intercept that traffic. From there, Envoy is going to look at that request that came through. Again, it's not connection, but request, and decide where it's going to load balance that. And there's kind of a hierarchy that we're going to go through depending on how much about the traffic we understand. So suppose it's HTTP. We understand HTTP very well. We're actually going to look at, for example, the host header. And we're going to, based on that host header, make a load balancing decision across everything that I know, all the backends that I know host the service behind that host, behind that host name, a DNS name. If it's only, for example, TCP traffic, and we don't have an HTTP, authority or host header, then we're going to look at the SNI, and we're going to use the server name indicator from TLS as a host name, and we're going to use that to make a load balancing decision on the connection. And if we can't do either of those, we don't have an L7 protocol that tells us what service, and we don't have an SNI that tells us what service, then the only thing that we have left is to look at the IP address and try to understand it as a VIP, and then do a reverse lookup on that VIP to load balance it. And if we can't do any of those, then we'll either drop the traffic on the floor because it's not discovered, we don't know where it goes to, or we'll just forward it transparently, and that's for you to decide. In general, for a secure and safe installation, we recommend that you drop the traffic on the floor. If you haven't modeled it in your service mesh, either as an external service that you egress to, or as something internal, then you probably don't want things transiting to it, right? This is one of the ways that we can control egress, for example. And so Envoy is going to forward that request on to a backend instance of B that it picks. And on the receiving side, we're going to apply policy. That policy, first off, we're encrypted in transit, right? So mutual TLS happens here. And A's Envoy presents a client certificate to B, right? And that is the identity of the client that's trying to connect to the service. The server, then B sidecar, looks at that client identity that came in and can authenticate it, and then can apply an authorization decision to say, is A allowed to call me or not? At that same time, we can apply other policy too. So rate limiting policy, other things like that we might want to apply on the server side get applied here. And assuming the policy checks are all good and they pass, then we're going to hand the request back into that service B. And it's going to do whatever it needs to do, right, to be able to process that request, whether that's other calls back into other systems, whatever it is. And then when it finishes, B is going to return that response. Both of those responses are going to flow back over the open connections through those envoys, although they're not going to apply any policy this time. They're really just gathering telemetry data. And then asynchronously and out of band, Envoy is going to report back data about what happened, whether that's traces that go to a system like Zipkin, or whether that's metrics that go to a system like Prometheus. They're going to report back that telemetry. So again, just to summarize, there's kind of two moving pieces. There's the control plane, that's Istio, that pushes configuration and identity to a whole bunch of different envoys. And then there's Envoy that's deployed one instance of Envoy for each instance of your application that's doing all of this functionality, service discovery, load balancing, resiliency, telemetry on behalf of those applications. Now, there's a whole bunch of different questions here. Let me address some of these before we move on to the next section. So one of them is, how do you manage the life cycle of policies that are in the service mesh? So fortunately, Istio's policy is all of its configuration is declarative. And so you really treat this as policy as code, right? And you use a CI/CD system to deploy that policy and keep it up to date with your source of truth, which should be some Git repo somewhere. That's the most common place that we see, and that's the most common scheme that we see for managing policy lifecycle and upgrade. That makes it pretty simple. We have a full history in Git. We have audits, we have the approvals and all of that. So if you're already going down a path of infrastructure as code in your organization, treat your Istio security policy the same way, right? Hopefully this also touched on, there were some questions around MTLS and similar. Hopefully we address those. If not, please ask more. And then finally, we'll talk a little bit more in a little bit around how we integrate external services in the mesh. But one of the other ones is like, how does this start to integrate with things like AWS Lambda and AWS API gateways? And that's, again, another piece that we'll dig into a little bit more as we get into the architecture of the system. It'll be a little bit clearer how these pieces fit together. And sorry, I'm just... insider threat detections are integrated in envoys. So how does Envoy do, request detection and similar, or threat detection and similar, right? So at a baseline, Envoy itself is not going to be doing insider threat detection, right? Instead, Envoy gives you a policy enforcement point. This is going to be a key that we'll talk about in a little bit, and I'll be talking about in my whole talk tomorrow, is the idea of Envoy as a universal policy enforcement point that has telemetry, data, and it's in the request path to be able to enforce that policy. So for a question like, how do I do insider threat detection? The answer is you plug in whatever system you want to do a risk-based evaluation of that traffic, and Envoy can be your hook-in point to enforce the verdicts of that risk-based system. And what's more, it can even feed that system data at runtime. And we'll talk in a little bit about the Envoy external authorization API, which is how you would plug in that. A couple other questions around some of the Cypher suites and different things are in Envoy. Envoy uses boring SSL. So the full set of Cypher suites you may know or be familiar with are there, including all of the FIPS Cypher suites. DNS poisoning is another really interesting one, and I'm sorry, there's a bunch of different questions here that I'm going to address because this is a good time before we go into the demo more heavily. So how do you prevent DNS poisoning? The simple answer is that the service mesh does not use DNS for anything unless you explicitly configure it to use DNS. Instead, Pilot or Istio's control plane actually pushes down the individual endpoints of all the workloads that it knows about to Envoy at runtime. And so Envoy itself, I said it looks at that host header, it actually ignores the IP address that your application depicts and instead forwards the request to a specific, and instead uses its own pre-populated service discovery information to forward the request on. So it doesn't look at the IP addresses that your DNS system is returning, and we don't use those at runtime in general. And so that's how we kind of sidestep DNS poisoning. The other thing is that actually Envoy is intercepting DNS requests and is answering DNS requests based on the service mesh's understanding of the world. So there's actually a lot of scenarios where your application is never going to hit an actual DNS server because everything can happen inside of the mesh. How do we replace some ingresses? We'll talk about that later. If identities are, how does the identity generation work? We'll get into that at length as well. But the short answer is that we try to use an existing platform identity that's there. And if not, then we at least use something from the platform to bootstrap it. But the identities are deterministic, and the identities that you get are, what you configure. So in Kubernetes, the identities the service mesh provides are based on the service account that the pod is running as, because that's the platform's primitive notion of identity. And I don't mean that as in the identity is primitive. I mean, it's the primitive building block in the Kubernetes platform for identity. And so we assign that service account. Therefore, anything with that service account, you could write that policy that says that this service account can talk to things with that other service account's identity, or how we phrase that policy so that it can go. And is this like HTTPS anywhere? Yes, this does do HTTPS everywhere. However, it does things besides HTTP, right? So we can go and upgrade any communication to encrypted, not just HTTP. How do we address replay attacks? That's a side effect of TLS, right? So TLS specifically has safeguards built in against replay attacks. Because everything in the mesh is encrypted with TLS, you get the automatic replay prevention there. Now, if you have a compromised workload, somebody's acting as your application, there are still avenues that at the application level they can do replay. But pure replay based on network capture naively is not possible because TLS specifically prevents that. And then there's some other things that we can do to prevent other types of replay based on end user credential based policy and things like job validation, things like that. Is Envoy replacing kubeproxy? Yes. Istio's with the CA, we're issuing certificates for Istio for workloads in Istio. Does that have to be self-signed? Out of the box, and by default, it is. However, we don't recommend that. You should issue certificates out of your existing PKI. Whew, all right, so with that, I think we got a lot of these questions. There's still a few more. Oh, there's just a handful more. Sorry, let me get these. Slides will be available. Things like WAF capabilities are actually there in Envoy today via mod security. And so you can even start to do things like WAF there. I think we'll actually demo some of that for you. We'll also demo some API gateway functionality. And so this is a great question. Somebody just asked, what about an API gateway in the service mesh? We're going to show you today how what I would call the 80% use case of an API gateway can be covered by the service mesh. And so let me just break that down real quick, and then we'll dive into the next section. So the API gateway, if we talk about the 80% use case and the 20% use case, the 80% use case in my experience is token validation. Validate my API key or my JOT token or my end user credential, whatever it is. Apply rate limiting to it, and then forward it into my application. Right, do load balancing. And that's the predominant use case for API gateways today. The service mesh can do all of that today, and we're going to show you that. The 20% use case, which is that heavier grade payload transformation, request mediation. One request goes in, let me split it up into 3 requests on the back end, stitch your response back together, and you hand it back. And the API portal. So that stuff is not natively addressed in the service mesh today, although certainly a lot of that stuff is coming towards is being pushed into Envoy. So there's not a really compelling reason that they need to be a strong, 2 separate layers for most of your applications. We'll dig into that a little bit more. And with that, I'm going to hand things over to Adam to set up some of the demo, and we'll get into actually showing y'all some of this platform in practice.
Good deal. Thanks, Zach. Great amount of questions, and let me see if I can figure out how I can get my question, the chat, to still pop up. I don't know how you're doing that, Zach. I can't see that, so you might have to jump in.
Yeah, I'll jump in and interrupt you with questions. You're not going to be able to since you're sharing your screen. I was just sharing one window. I was cheating.
Gotcha. Yeah, and also I'll be typing, demoing on the command line in the browser. I probably don't have the skills Zach has to answer questions as I'm doing that. So keep them coming, and we'll try and get through that. So today's the bulk of the rest of the session is, as Zach kind of said, going to be show and tell, showing some of these building blocks, security primitives that service mesh gives us within our toolbox to start to employ within our platforms and within our applications. So to give you the macro level view of what we're going to be working with, and I think Zach alluded to this, we have 5 different Kubernetes clusters spread across 2 different clouds. So we have some that are in Google Cloud, others that are in AWS. We have some that are using the managed Kubernetes services from AWS and Google, and then some are just simply using the raw compute and then have instantiated something like OpenShift. And then 2 of the clusters, the ones we'll primarily be focusing on, are actually stood up and have the componentry of the Platform One Big Bang platform there. And we have a couple sample applications that we'll be demoing, showing how we can control ingress to these applications, how we can control east-west traffic, bouncing across clusters, failing over. As you see in one of our Big Bang clusters, we have a few services that are running on a VM that we're going to onboard. And the important thing, I guess I'll point out, is we'll be touching actually 3 different layers. One is the application edge. So how at the far edge do we intelligently understand our services across a heterogeneous compute environment spread across multiple clouds? How do we transit from that to actual ingress into a contextualized Kubernetes cluster that is running our services? And then finally, how do we actually get that traffic and control that traffic and secure that traffic to our specific pods, go from pod to pod using the service mesh? And maybe that's a little bit of a misnomer, because this all is stitched together into one large mesh. So the first thing I wanted to show for you and talk about for just a second is the primitives of multi-tenancy. Because up until now, Zach talked about service A talking to service B. In reality, it's far more complex than that. And that's actually also the physical manifestation of our services. Enterprises, organizations don't think of their applications in just Kubernetes pods or VMs. They think of it as teams that manage services, that deploy these services across logical environments. And so there needs to be some sort of notion of how do I slice this up and match or map the logical constructs that organizations have for how they organize their application development teams, and also the roles within those teams, to the application of the configuration to the physical environments that we've talked about thus far. And so with multi-tenancy, we want to make sure the teams have the contextualized view of the services they care about, and then the people with the correct roles can configure the correct things and give them the actual RBAC controls to ensure that security architects can control things related to MTLS and certificates and policy, whereas they don't really care about something maybe like client-side load balancing. And we leave that to maybe the application ops or the DevOps role. So within the platform, we're going to demonstrate that, or I guess I should say, this is a different representation of how within TSB, Tetrate Service Bridge, we think about those constructs, going from a team who is going to manage a workspace, which is a construct of, hey, here is an application that a team might own, to finally the backing infrastructure, the backing clusters and VMs that are associated with that application. And I'll point out here, you'll notice it's not always a one-to-one. So in this illustration, team 1 and team 2 happen to manage an application, so they're given a logical workspace, but team 3 actually owns a couple applications. And so they would be given access to a few different workspaces. Now this hierarchy, this model, then gives us the ability to start to inject policy, and again, give controls to people who are part of a tenant or a workspace, access to the right config, the right policy they want to author. So there's really 3 important constructs that we'll see as we go through the demo. First is a tenant. That's most tightly bound to the actual team. A workspace represents typically the application they own. And then these groups that you see depicted here, a gateway group, traffic group, security group, allow us then to provide access to the configuration that are described by those nouns. So security group, that's going to give you the ability to author security-related policy. Traffic group is related to client-side load balancing, so that's going to control how traffic flows in and out of your specific pod. Gateway is more associated with ingress. All these then are mapped to the physical infrastructure using tuples of selectors. So basically the cluster namespace that they live in and where wildcards are supported. So potentially where your mind is going, or where this then can illustrate the power of what you can do, is at all these layers, we have the ability to inject policy. It could be very specific policy for this microservice. This is how I want traffic and security configured, to potentially at a higher level, which would allow us to set default policy. And that's what I'll really focus on for the most part with the demo, setting a policy that says within this application, all traffic, regardless of what anyone lower down the chain says, I need it to be MTLS, strict MTLS, or I need to author specific authorization policy that dictates who can only communicate with me. And it all then cascades downward, southward, to the actual instantiation of services that are under these granular building blocks. So what we'll see in this demo, right, we have a tenant, so we're going to pretend we're all 400 of us, part of one application development organization. In this demo, we develop a couple different microservices applications, a book info app and a demo app, and then we have those groups underneath. And so we're going to apply a policy to our applications and also see how, as an app owner, we can apply global policy to our book info and our demo app that has a front end and back end. So with that, let's first get into the application and set a little bit of a workspace for us to operate in. So I'm going to log first into Tetrate Service Bridge as administrator, because I want to first give a correct group or set of users access to these tenants. So I need to make a mapping of who actually is part of this NIST tenant. So as I log in as an admin, you'll notice I have 5 different tenants here, a couple related to just random things. We're going to focus in on this NIST demo tenant. And then as I showed in that slide deck, those slides, these tenants then have workspaces which represent the actual applications that are deployed within them. So this ops one has a little test app workspace. But again, we're going to focus on this NIST demo workspace, which contains our 2 microservice applications. So the point of showing you this, though, is that we want to map who actually is part of this tenant. So we can say, let's pretend that our platform team owns these applications. So we're going to provide a mapping that says anyone who logs into the system and is identified as the group platform group are going to have access to this. Now, this is backed by a little demo LDAP server that I have. Typically in the real world, this would be plumbed to whatever sort of identity provider your organization has. And then we'd be syncing and pulling these in.
And one thing I just want to call out here real quick, we mentioned that one of the things we do is collaborate with NIST on access control and next generation access control specifically. That's actually what underpins all of this stuff. And so in a little bit, Adam is going to show you, kind of logging out and logging in as different users, and how that changes what we can and cannot do. All of this under the hood is actually powered by next generation access control, which we've been working on with NIST to be able to do things like who can access what, and the full tenancy and resource hierarchy is built out using that capability.
Okay, great, awesome. Thanks, Zach. Yeah, that's actually where we're going to go next. So I've kind of set up everything as an admin. Typically, as I said, this would be plumbed with your identity provider. You probably would have some sort of onboarding automation that says, hey, I'm onboarding a new tenant, and I'm going to automatically link all this up. So in reality, you may not manually do what I just did, but I wanted to prove the point of how we have this tenancy mapping. So now I'm going to log in as a user that's part of that platform group, NACX. And you'll notice when I log in, now I only see the NIST demo tenant. I don't see all those 4 others. And I get right into my workspaces, my applications that I care about. So let's talk about now next what we're going to actually get into with controlling our services with the mesh. So we're going to talk about how we can do multi-cloud, multi-cluster routing, apply security policy, and then we're going to introduce some VMs into the mix with this. So you probably recall this slide that was shown before. all the features of what a management plane bring in, one of the most complex things that gets introduced as you start to manage your services across multiple clouds, multiple clusters, and potentially the heterogeneous compute of your VMs is how do I reason about and consistently deliver configuration, the routing configuration and endpoints of how I make my services resilient and highly available across all these different compute platforms. And then also, how do I deliver policy that dictates who can talk to who via MTLS, and then have some sort of a simple way to automate the distribution of this to n number of environments rather than having to create a bespoke pipeline for each one. So that's the role of a management plane in this architecture, and the role of TSB for this. Now, when we talk specifically about how do we control and shape traffic, the primary responsibility of a management plane in this context is to deliver the proper configuration that's contextualized to a cluster, and then configure the constructs within the service mesh that allow us to shape traffic, configure where endpoints are, configure services discovery and whatnot. Now, what do I mean about proper config distribution? Well, if you look at this diagram, we have 4 clusters here. And if we go back to that multi-tenant model, we're depicting 2 workspaces, so 2 different applications that ultimately are concretely going to be bound to a namespace. And so if you look at what's deployed to our clusters, some clusters have both services, other clusters only have one service. And so when we talk about distributing the proper configuration, what is delivered to cluster 1 that helps us shape and map traffic and route traffic as our services communicate is going to look a little bit different than what lands in cluster 2, simply because our workspace 1 microservices applications don't exist there. So when cluster 2 needs to discover them, needs to route them, that path, that configuration that dictates that is going to look a little bit different. And that's just an example for shaping traffic, but we could go down the line of policy that's security related, auth-in, auth-z policy for that. And so as we introduce these clusters into a overarching management plane, which is what TSB is, it starts to give us some great benefits as we go multi-cluster, because there was a couple of good questions previously in Zach's portion about like how do we manage these certificates, and I think also maybe what you're getting at is how do we actually define trust across all of these clusters, and how do we ensure that trust domains are established properly. So the role of this management plane is to ensure that each cluster can potentially trust each other, and we can create connections that are going to be mutual TLS between them, give us semantics to all author cluster to cluster permissions that would dictate, can cluster 1 actually talk to cluster 2, or a subset of apps within cluster 2 talk to a subset of apps within cluster 4, and then propagate all the routing information about what application lives where. So when our application that's in blue in cluster 2, so that's part of workspace 2, when it has to say, I need to make a connection to my application from workspace 1, it knows where that lives, it knows how to connect to it securely via MTLS, and it knows how to verify the identity that it's going to find on the other end of those certificates. And so what architecture this is moving us towards is an architecture in which application teams now start to really take ownership and control their gateways and the primitives for which they can control their ingress traffic. And so we start to see a pattern where each application has their own dedicated gateway, and then they are able to use that gateway in the underlying mesh for the constructs of how do I route, how do I do authentication and authorization, both service to service and end user, how do I start to author some of the policy that I like to dictate for client-side load balancing, and also how do I intelligently discover and route services across the mesh. And that's what we're going to go into next. So we're going to see a demo. Imagine we're going to kind of be this application in the consumer namespace. And when possible, we want to connect guys that are potentially in our cluster, potentially on the same host, And only in the case that there's failures would we fall over to a different cloud. So let's get into that portion of kind of this interactive demo. And as I go about this, Zach, definitely jump in and interrupt if there's questions about what we're talking about.
Yeah, I'm answering a lot of them here in
oh, awesome. Good
so
deal.
none of them have been too, but I'll definitely jump in with the heavier ones.
Okay, cool. So we're going to first focus in on this book info application. That's kind of the canonical Istio demo application. It's constructed of 4 different microservices that are all stitched together by a user interface to give us the details, reviews, ratings of our Shakespeare book here. So if I take a look at this book info application within TSP, again, this is sitting in its own workspace. First thing you'll notice, I can get a dashboard. Let me take off the services we're not demoing here. I can get a dashboard that gives me the golden metrics that I would like to know from an observability standpoint. How is my service responding? What is the number of requests flowing through the system? What is my error rate? I'm also able to start to gather, and right now everything's healthy, a topology graph that shows where services live, who's calling who, and potentially most importantly for this context, who's calling who over secure protocols or using something like MTLS. And so as I kind of set up our demo environment, you'll notice this is a Big Bang cluster running in GKE. Unfortunately, Google and Amazon chose very similar logos. This is actually EKS cluster running in Amazon. I think down here we have a second Big Bang cluster. Then lastly, this is OpenShift. And we have the exact same copy of our application running in every cloud with an edge load balancer, which we call a tier 1 load balancer that's spreading traffic, basically serving as the ingress point of my application I just showed you. One thing I'll point out to go in harmony with what we're just talking about with locale-based routing and intelligent routing, you'll notice that even though I have a version of my service in every cluster, once I start to land in the cluster, in this case, my Big Bang cluster, I'm not going to start to bounce around to, like as a product page tries to get reviews, it's not going to go across to Amazon or go to a different cluster. It's going to keep it local unless there is a failure. So let's actually simulate that failure. What we're going to do is pretend that this detail service, for whatever reason, goes poof, it dies. We lose that in our Big Bang cluster that's in, I believe, GKE central region. And to do that, we're going to just simply scale the deployments of this kind of a contrived failure that we have, but this is going to bring down our pod. Now, we will notice with our application, we shouldn't experience any failures, right? As if we continue to refresh this again and again, we wouldn't lose details. Maybe every once in a while, we'll see a few extra milliseconds of latency, because what will happen is once this guy disappears, then we'll have a failover. So by refreshing this, we'll get a new set of metrics, and from the outset, you'll see immediately, well, it's going to tell us our book info application, the detail service in our Big Bang cluster is unhealthy, depicted by red here. Though we have metrics from the last 15 minutes, we have 0 instances running. If I take a look at the topology view, we'll see there's now a new line. Let me kind of rearrange these so it's very clear. Whereas before we saw all traffic staying within the cluster, now since there's a failure, we see our product page bouncing over to our other Big Bang cluster. And this is because I've authored traffic shaping policy that says when there's a failure, don't just randomly send the request to a different Kubernetes cluster. I specifically want to shape this traffic to only fail over, in this case, to our Big Bang cluster in GKE. If this guy also failed, then I would go to a different cloud. But I'm able to have that fine-grained control. And you also note, because of my failure, I do see a little bit of a color change in my gateway, indicating that, one, there was some latency, and maybe there's a couple connection resets in which we had to retry the requests in this case. Now, in this instance, right, we had a pretty complex application. It's all set up already. I'd love to show you how simple, though, getting that ingress is into our cluster. Because as we recall, we were kind of talking about application teams controlling their own destiny, being able to have a paved pathway of how to safely and securely build up their own application ingress. So I have another application that we'll kind of use throughout this workshop that does not have that configured yet. I don't have anything listening and handling my requests at this demo app URL. So if we go into our other application, which we've named front end back end, into the configuration that houses our ingress gateways, we're going to create a new gateway here. And we're simply going to instruct our clusters how to receive this configuration. So this namespace that this application lives in is in demo app. And I can give it a selector. I'm going to copy and paste because bad things happen if I have even the slightest typo. So we're just simply telling it where is this ingress gateway live in this case. And then I'm going to tell it what to listen for. And again, a slight copy and paste of a longer URL. So this is a host name I wanted to listen at. These clusters are plumbed with external DNS. So as this config is pushed out, DNS will automatically be registered. Our name is going to be demo gateway, listening on a secure port. We're going to just do from the ingress gateway standpoint, just simple HTTPS. And then lastly, we just simply tell it what is our backing Kubernetes service in this case. So I tell it I want to simply route to a service, which is sitting in my clusters. And this is going to be my demo app front end. And so by saving these changes, what this does is says for every Kubernetes cluster that's onboarded into this front end, back end workspace, in my case, it's just one, but if I had multiple, it would blast that configuration out to all these namespaces and pods and ingress gateways there. So with that taking place, my application now is receiving ingress via TLS. And the interesting thing is this is a little demo application that allows us to now sniff around the mesh and give us a good entry point to just to demonstrate some of our security constructs. Because what this does is make a request not through my browser, but through the mesh to services that I can discover and connect to. So this is a little backend pod that's running in the same namespace. I can connect to our product page service that's in our book info namespace. This guy's on 9080, right? So I can kind of start to explore my global mesh, and here's where it's really interesting that we can start to apply some of the security policy that you all are probably most interested in seeing that we can use the mesh for. So before actually starting to apply that policy, let me jump back briefly to the presentation and kind of talk about what are, yeah, go ahead, Zach.
Yeah, I was gonna say, before you get into that, sorry, let me interrupt you real quick. There's just been a couple of different questions that I think we should answer real quick.
Sure.
So one of them is, hey, you have that central management plane. Is that involved in multi-cluster failover and like some of that multi-cluster traffic management? Like, how does that work, right? And the answer there is that no. Fortunately, it's out of band. The management piece is really only for humans pushing intent into the system. At runtime, it's totally out of band, right? One of the other big questions is, and I've seen this maybe phrased a couple different ways. So one of the questions is like, hey, are these gateways scalable? One of the other questions was around the Envoy sidecar footprint and some of that. So let me just address that real quick before we dive in. Sorry. And so in general, Envoy is a really, really lightweight proxy. And that's one of the reasons we picked it. So first off, everything that we're showing in this demo is horizontally scalable, right? So in terms of, hey, are these gateways scalable or not? Yes, both vertically and horizontally. And Envoy instances can be scaled vertically to take advantage of more cores, more compute. And you can always scale them horizontally, have more instances of them to serve that traffic, right? In general, an Envoy sidecar is really, really lightweight. It takes one vCPU, we can do roughly 3,000 requests per second with about a 50 megabytes of RAM overhead. So it's not that it's a pretty lightweight proxy to run there. So I just wanted to kind of underline that as a background here. One of the other questions was, hey, you're showing a bunch of stuff in the UI. Do I have to use a UI? Can I use Terraform or others? And the answer is yeah, 100%. And that's the way that we see people use it, and that's the way that we recommend folks use it, right? Is treat your infrastructure as code, treat all this configuration as code, use a CI/CD system to deploy. Sorry, I wanted to, there were just a couple questions in that vein. I wanted to get in there.
No, thanks for answering that. Yeah, and maybe I took the incorrect guess, but this might be less interesting if you just saw me pop open a giant terminal and do a bunch of YAML applies and showed my YAML editing skills, because ultimately all these objects that you have seen in TSP and that we're demonstrating. In fact, if I go back to what I just authored in my gateway, I very well could have authored a little YAML file that looks somewhat like this. I wouldn't need all the default settings that are empty, but I could have authored that, stuck it into Git or some other version control that you've chosen to use, and have something else that then applies this. And you'd have a workflow around who would approve that and whatnot.
Exactly. And sorry, one other thing, Adam, is just somebody bumped in and said, hey, this seems like this makes network segmentation really trivial. Yes, that's the point. And in fact, we'll talk about that in just a second, because you see maybe one of the bullet points there that is L7 microsegmentation. And so, yes, that's exactly the goal.
Yeah, and so if with this little bit in the demo, I'm not sure who asked that question, but if it doesn't click of how simple it can get, definitely ask a follow-up question. Zach and I will address that, because the goal is exactly what you said. This really makes microsegmentation very easy, and it's going to be based on the identity that's associated with an application, rather than raw descriptions of IPs and things like that. So some of this is kind of reiterating what we heard Zach talk about earlier, with what is some of the problems with moving to cloud native, and some of the overarching goals of someone moving towards a more secure, moving towards a organizational strategy of zero trust. What they really care about is, how do I encrypt all my traffic? How do I ensure every player within my ecosystem, every service, has a strong identity that's cryptographically verifiable, and that will follow along my service? And then how do I start to author policy and control, or how do I microsegment my traffic using the characteristics of that identity that's going to follow around my service, and then contextual information of where that is running, with actual attributes, if it's a layer 7 request, attributes of the request. And so if you boil that all down, it's, how do I authenticate and authorize my traffic? And then the third A in this AAA support that you see mentioned here is, and how do I actually prove that I'm doing all the great things that we're talking about? How do I audit and prove that we actually can report that, yes, we have these controls in place. Yes, all of our traffic is encrypted. Yes, we have authentication and authorization in place. When a rule changes, who changed that rule and whatnot. That's the whole role of this management plane. And you see in the footnote, Zach, who's been chiming in, has co-authored really the authoritative paper of, here's how to implement these items. Here's all the things you should do if you're building a cloud native application with the service mesh, and how to make it secure. So it's much more complex than simply saying we're going to authenticate and authorize. There's a whole bunch of recommendations that really should be incorporated as you design and implement this within your environment. Now, again, as I stated before, this is all well and good. Where it gets complex is when you start to scale across a whole bunch of different applications and a whole bunch of different compute infrastructures and a bunch of different clusters. And how do I make sure all this is taken into account as I start to author this policy? And then also, how do I enable those who might want to control global policy versus lower down the stack application policy? How do I ensure the precedence that InfoSec is able to have their policy go in and app devs can't override that? And so that is what is the role of a platform like TSB, the role of something that's a management plane that is overarching across all of these. So it gives me the semantic to say, I'd like to describe my application one. It's a secure application. It's spread across a couple clusters, potentially even across VMs. And here's some policy I'd like to apply to that. And same with my other workloads that are going to be deployed. At the same time, we can have a higher overarching policy that says, if you are of this type of app in this type of tenant, I want to have something like strict encryption, strict MTLS always turned on. And I want to make sure my traffic flows in a very specific way, and not allow app teams to override that. Now, I've talked a bunch about the authentication and authorization tied back into the identity. A key to doing this correctly is ensuring that that identity is going to be rooted in a way that all your heterogeneous compute, all your clouds, all your clusters are able to understand the identity that's presented. And the key to doing that is ensuring whatever identity provider your organization has selected is the issuing authority for these cryptographically verifiable certificates that go into that spiffy identity that Zach mentioned. These are the building blocks of then authoring that policy that allows us to shape the traffic and control who can talk with who. And so we can do that at the service to service level. So this isn't even taking into account the end user. Simply say that this application can or cannot talk to other microservices, and automatically that configuration is propagated to all clusters, such that when an MPLS connection is established, will authenticate and authorize based on those identities that are provided. In this case, it's illustrating the fact that these two applications should not be able to talk to each other, and we've authored policy that way. And then secondly, we can look at the actual requests if they are coming in with user authentication information, and actually look at something like a JOT token and author policy that not only authenticates the traffic between the services, but then is there a request and its identity of who's issuing it trusted at that user level. And that's going to be connected into whatever sort of identity provider, again, is chosen by the enterprise. The sidecar will intercept that, verify that JOT token, and reject it, not even let it reach the application. Or if it's authenticated, it can still give those tokens to the application to change its behavior, or the application to take that into account. So let's begin to author a few security policies for our application that we have deployed. As we had demonstrated, we have this application that's kind of handy, allows us to poke around our service mesh. I actually have a version of this application first that's just a raw Kubernetes service. I don't even have certificates. This is HTTP traffic. So this is a pod running in a namespace. It doesn't have Istio injection enabled, which is a flag that's required to introduce it into the mesh and have sidecars added to it. So it's running in this no mesh namespace. So it's basically an external actor to the service mesh. Right now, we don't have any policy, so I can call my backend demo app application and get this wonderful cat picture. So I transited, entered the mesh. I didn't present any certificates. This is actually just raw HTTP traffic, but I was able to make this request. So at the outset, that's terrible. We don't want that to happen with our application. So using these default policies, I can author policy for, again, going to my workspace. This is my front-end, back-end application, the workspace that's controlling that back-end application as part of the mesh. And I can, author default policy here. Again, UI is a little more simple for explanation purposes than the CLI. This is just YAML that gets created under the covers. So I'm going to say when services call me, I'm going to require an TLS certificate with identity to be presented. Not even going to do anything for authorization. You just simply have to present a valid certificate when you call me. That's blasted out. It took maybe 1 second to propagate to all my clusters. this connection reset is indicative that I was rejected because of my identity or lack of identity with a certificate. So that's great. We've enacted some controls over our application, but if you recall, we could call our book info application here. So this is traversing basically two different app groups. So this is one application. I'm calling it from my front-end application. Let's say we actually have to author not only authentication policy to say we want MTLS to be enforced, but also we want to authorize requests that are going to come service to service. I can use TSB to author that policy also. So I'm going to go now into my book info application and similarly create some default settings. I'll ensure that people present a certificate, but I can say also authorize requests based on workspace. So this is using the semantics that developers, application teams are probably going to be familiar with, because a workspace, again, is where their application, their little playground that they have here. And so what this does, it says only applications within this workspace, which are going to be just my book info applications that are spread across all 5 of these clusters, are the only identities that I'm going to trust. So essentially kind of building up this model where I'm saying, for whatever reason, app 1 is secure, I'm authoring this policy that's going to make it so. I hope I clicked apply there. Let's double check that. Yeah, I did. Save those changes. And so now this should start to get rejected, right? So now I got an HTTP 403. The sidecar rejected me because I presented my certificate, but I wasn't part of the correct workspace. And then the textual message that's access denied. The last bit that typically is going to be enforced, you heard Zach talk about the best practice of making sure you understand the flow of all your traffic. And if we can't resolve, we don't know where traffic's going, potentially just drop it on the floor or block it. For requests that leave the cluster, that is certainly the case. For egress traffic, we want to have fine-grained control over that. So I'm also able to author similar policy that will be pushed out at the workspace level. So all applications that have some relationship to a workspace, egress policy that will basically allow me to allow list or at least control how traffic leaves my cluster and leaves the mesh and traverses elsewhere. Since this little front-end application is the best one to test with because it allows us to kind of poke around and do some HTTP tests. So I can leave the service mesh, go to something like google.com, or in our case, probably best for this demo is we're going to go to nist.gov, and we can go to the beautiful NIST website. Looks like some CSS is messed up because of my sample application, but I'm able to go to this website. But as you saw, I could go to Google, I could go anywhere because there's no policy in place. So I'm able to author that policy, similar to where I said I'd like to control security. I can also set default egress policy here. I'm going to copy and paste my gateway because it's a little bit of a long host name. I'm simply telling the mesh now for all outbound traffic leaving the sidecar proxy, here's where you need to send that traffic. This is my egress gateway. The egress gateway itself is actually an Envoy sidecar. It has those policy and rules defined within it. So if I change that, now my environment is 100% locked down because I don't have any allow list rules. So if I refresh that, now as I try and leave the mesh, I'm actually not allowed to make any requests outside the mesh. And so the next step is now start to have some sort of allow list rules that start to punch holes through that gateway. So I have a configuration object that I can start to author this policy. So we'll say star.nist.gov is an allowed endpoint. I'll acknowledge this is somewhat contrived. This is probably going to be your backend databases, your legacy systems that are not being modernized and introduced to the mesh quite yet. You want to author this policy to allow specific applications or even specific identities within the service mesh to connect to this. This rule right here is allowing everyone within this workspace to talk to this endpoint, but I very well could limit this to certain service identities as presented by the service account that's attached with your service. Now that I got that in place, now we can get back to our beautiful NIST website with the images that got stripped out by my sample application. So we're able to connect there, but something like Google.com is still going to be blocked because I didn't allow that. So we've started to implement some security controls around our application that allow us to have a declarative way that we're controlling authentication and authorization at our service level, and then also starting to control and shape the traffic that's leaving the mesh. So the last bit I'd like to talk about, and I think this might generate a little bit of discussion, probably in the chat. I think there already were some questions of how do we start to bring aboard other external services into.
Yeah, that's exactly right. And in general, hopefully that also helps. Hopefully this past bit helped explain a couple questions around how do we integrate third-party services? How do we manage third-party SaaSes? How do you manage second-party partner APIs that you don't control? And the answer is using exactly what Adam just showed. It's how we would start to control how we communicate with those services that we don't own and manage. Now, what he's going to show is how we can start to pull some legacy applications that we don't typically think of as belonging to the mesh into it. So kind of the other flip side of not treating them as external services, but actually bringing the mesh there.
Yeah, and actually one thing I'll add to what Zach mentioned, I didn't demo it or touch on it just simply because of time, but that is actually one of the, adding external services or external parties, specifically when you want to do something like MTLS with those third parties. What I just demonstrated didn't do MTLS, but we could have very easily had that egress gateway, look at a connection, write it with a specific identity and a specific certificate, and connect to that outside party off the mesh using MTLS. You now have one central control point that you're controlling that connection versus every app team having to wrangle, well, how do I call out from my Java app or my Go app or my Ruby app, load in the certificates, do the crazy Java trust store dance, and it just gets complicated so quickly. Having it at this one point makes calling out securely to third-party apps, third-party services with something like MTLS very, very easy.
Yeah, and we see this all the time. Just to touch on that a little bit more, the general phrase that we use for that is credential exchange, right? So when Adam talks about MTLS from the egress proxy out, we don't mean the mesh MTLS that we've been talking about so far, right? That's for internal communication. That could potentially even be a self-signed certificate for that one cluster if you really wanted it to be, but we don't recommend that. What we're talking about when we go out to egress is having the egress proxy hold whatever the credentials are that are needed to talk to the external system, whether that's a client cert because it's a second-party API that you do MTLS with, or maybe it's like an API key or something like that. And so what we can do is have MTLS with the mesh and with those strong identities and with that strong security policy that Adam just showed for communication between services in it and for communication between a service and the egress proxy. And then the egress proxy can decide based on the identity that's coming into it from the mesh internally, when it goes and forwards that call externally out to google.com or to nist.gov, it can pick the credentials that it uses to make that call. That's incredibly powerful because it gives you a single set of locations to allow for firewalls, right? Your egress proxy, not all your applications. And secondly, gives you one place to have those credentials, exactly like Adam said, so you don't have that burden of management across all your applications.
Yeah, awesome. Cool. So kind of the last one of the last pieces of the puzzle that's probably the most important, because the reality is most of the things that probably make the money or protect our government, if you're part of a government agency, the key applications are probably not cloud native applications quite yet. And the question is, well, how do I start to introduce some of the primitives that I'm moving to cloud native for, such as faster failover, intelligent routing like I demonstrated, better security primitives, canary rollouts. How do I do all that, but also extend that into my legacy applications? Or how do I ensure that as my cloud native applications connect to the really important things, how do I get things like MTLS and policy as close to that application as possible? And the solution is introducing those VMs or those legacy systems into the mesh. So you're able to build an architecture potentially like what you see here. Some cloud services where you're doing traffic shifting, traffic splitting, but part of that traffic shift is going to your on-premise cloud or the raw compute that you're vending from a public cloud, and these legacy services that are just on virtualization technologies or potentially even bare metal technologies. I guess I could use those interchangeably. Anything that's not Kubernetes native quite yet. So the technique to do that is simply to get an Envoy sidecar as close as possible to your application process. Typically, that's going to be on the VM itself or on the workload unit itself, but there are some patterns and some types of applications where that is just not going to be possible. So it could be just outside, but we want to extend the mesh as close to your application as possible. And then there's some important objects that then get introduced within Kubernetes and within your service mesh to represent these things that are not actually within Kubernetes, not actually within pods. And specifically, these are an object called a workload entry or a workload group. This simply represents a workload, as the name implies, that is outside of the cluster. And it has some instructions of here's where it lives, here's this IP address, and allows us to add some of the metadata labels that we typically have with Kubernetes objects to that external workload. Secondly, we have a sidecar. That's a declarative description within Istio. That's actually not just for VMs, but it's more important with VMs that simply gives configuration control to how that Envoy proxy behaves. And then lastly, we need to create a Kubernetes service that exposes the thing we want to expose. And rather than pods being picked up by Kubernetes and stuck behind as endpoints of that service, the endpoints of our workload entry become mapped to that. And then the act of getting that Envoy proxy, getting that VM onto the mesh is simply register as a workload entry and then bootstrap that VM, which really means get some configuration into that VM, security tokens, certificates, and the instructions of how it should operate, and then start up that Envoy proxy. And Tetrate gives you some tooling that makes that quite easy. One last interesting wrinkle is probably the case for the vast majority of your legacy workloads. They probably won't be able to directly address pods within Kubernetes using that pod IP, like most workloads within a cloud native environment could. If that's the case, there's one last piece of the puzzle, which is a VM gateway that will sit in your Kubernetes clusters that simply facilitates that communication back and forth. That allows both the VM to talk to the Istio control plane to receive its configuration, send metrics and things like that about itself, but then also allow it to communicate with other pods and services within the environment. So it's a pretty simple, or I shouldn't say simple process, but it's a clear-cut process to bring a VM into it. Typically, you have an original state of a VM fronted by some sort of load balancer. We're going to show this in Google Cloud in just a second. We introduce that sidecar. We start to introduce the VMs themselves into the mesh. And then lastly, you start to employ whatever sort of modernization pattern you have for your workload. Potentially you're strangling a monolith. Potentially you're just lifting and shifting that into a pod. A number of different techniques, but you introduce that then as a pod, a service within Kubernetes. Now you have all the flexibility of the mesh to shape and route traffic and control what that migration looks like. Whether it's certain users, whether it's a certain percentage of your traffic, whether it's based on a cluster, any attribute of the request, you can start to shape that traffic. And we'll demonstrate that in a second. And so let's introduce one of our services to the mesh. So thus far, when we've been working with our book info application, I glossed through it probably a little quickly, and you didn't pick it up. But if we actually looked at one of our big bang clusters, oh, let me scale up details back up to 1, so that actually will accept traffic. If we look at our big bang cluster where we did that failover, it actually doesn't have the service that is being used to give us these star ratings. That's actually on a VM. And we see that not listed here. Similarly, in the topology, we don't see our rating service showing up because, again, it's external to the mesh. We're just going to an IP address. Well, how does this work? Well, we have our application deployed and configured at a different endpoint, so I can directly address this one that's running in a specific big bang cluster. You'll notice it reports to me that this is the rating service is just at a IP address. This is an IP address that is represented by this load balancer within Google Cloud, within GCP, and it has an instance group that has 2 VMs tied to it. And these are the 2 VMs that I'm logged into here. For simplicity's sake, I have my application running a Docker container. Just for ease of demo, it would behave nearly identical if it was just a process running on the box. If I take a look at my logs of my rating service, we can see the health check coming from my load balancer. If I actually use this app a little bit, we'll start to see the ratings calls come in and hit my application. So that's why this application is still able to function. So we're basically in this swim lane, this original state. So to onboard, again, to reiterate what we talked about with the slides, I need to tell the service mesh where these VMs live via workload entries. I need to configure a Kubernetes service, and then I need to actually get Envoy running. And so these are kubectl apply commands that I will execute. First thing I'll do is I'm going to tell it where these VMs live. That's not the right one. So it's going to create those workload entries, those objects we talked about. I can ask Kubernetes to report back to me. This will give me just the important things. I don't want to share the full YAML with you, but it basically tells me I know I have ratings VM on these 2 IP addresses. This corresponds with these 2 VMs that you see me terminaled into. Next thing I need to do is create that Kubernetes service that is actually going to create a notion of my ratings service within Kubernetes, and thereby is going to be picked up by the service mesh. And it also reconfigures my application. So as soon as my pod starts up, you'll see that IP address now is going to discover the rating service at port at ratings 9080. It's not going to work quite yet because I haven't onboarded my VM, so I get it unavailable. But now we have to kick off that bootstrapping process. Before that, I just need to start my restart my container process. Restart. And what this does is going to stop my Docker container and restart it and simply bind to localhost, bind to my loopback adapter, because I want Envoy to actually now accept all traffic coming into port 9080, coming into my VM. There's a couple of different techniques. We didn't have to do this. We could use a different port, but for simplicity's sake, we're just simply going to make our application not listen externally, and we're going to let Envoy do that.
And in fact, actually, one step that would be even safer that we would recommend is doing it over a domain socket. So you're not even talking to the loopback or anything like that, right? And sorry, Adam, let me just interrupt you real quick here, because there's a couple different questions that have come in that are a little related. I think now's a great time to answer them. So one of the questions has been around, like, hey, where is the MTLS happening? Is it only at ingress or egress? Is it happening inside the mesh? And then by the same token, there's a separate question asking, how is that MTLS that you're talking about working? How hard is it to set up? Like, what does it take, right? And so now is the perfect time to talk about it, because Adam just did exactly what it took to do it, which is all he did was went and deployed the Envoy next to the application, whether that's on a VM where we have some tooling that we're doing it with, or if that's in Kubernetes where you're putting it next to the pod, where we use the Istio injection webhook and similar. At the end of the day, we're putting that Envoy proxy next to the application instance, and it is doing MTLS on behalf of the application with a certificate that is issued and refreshed by Istio without the application being involved. And so, like, literally, Adam just did that. Now there's MTLS on the VMs. That's it. That's what it took, right? It's actually pretty amazing. One of the other questions just that I'll talk about here is, somebody asked, what's a VM gateway? That VM gateway is just another ingress gateway, but it's specifically intended for use inside of the mesh by VMs. So it gets a little bit of different automatic configuration compared to what we call an ingress gateway, where you curate very carefully which services are or are not exposed, because that's intended for like external clients to consume, for example, whereas a VM gateway is intended for internal traffic. And then finally, there's a question around like, hey, are there issues with like kernel version on the host with VMs and similar? And the answer is that, if you're at least moderately security conscious, then you are running a kernel version that is recent enough for Envoy to work very happily. Envoy, and then when we're talking about older kernel versions, you're really just talking about performance losses, or rather, more modern kernel versions are going to give you better performance out of Envoy because of the underlying networking mechanisms that it uses, but you should not have issues if you're using, any kernel from the last couple of years. Sorry, I just wanted to
Yep. No, that's
hopefully
great.
y'all ask more questions. If not, and then ingress, and then the question on TLS. So the ingress and egress can do TLS for you. They can do MTLS for you. And then what happens is when they send traffic into the rest of the service mesh, they're going to do MTLS exactly like they're a sidecar in the service mesh. So hopefully, folks, this answers questions. If not, keep asking, and we'll keep going.
Yeah, awesome. Thanks. So to reiterate where we're at, we've told the mesh where our VMs should be. Right now, it's not able to route to it because we don't have a proxy yet. We've created the Kubernetes service, so theoretically, we should be able to route to it, but the endpoints are not responding. The last step of that process is to actually start our VM or bootstrap our VM so that process starts up. And as I mentioned earlier, Tetrate has a little, makes that simple. We have, as you saw, a CLI that will kick off that bootstrapping process. All that did is transfer some certificates and security credentials so that the VMs are able to connect to the Istio control plane, deliver it a little bit of configuration, and also start up that proxy. So now if I look at my Docker environment, I now have an Istio proxy running on both of these. And to actually get insight into what's happening with my application, now I can look at not my ratings service, but I could actually look at my Istio proxy here, and I'll take a look at that proxy in both these VMs. And now my application should be functioning, and it's fully onboarded into the mesh. As Zach was alluding to, we have MTLS all the way down to my proxy. Maybe not the most securely handing into my app in the loopback adapter. Domain sock would be better, but at least from our application all the way down to this VM is using service mesh MTLS certificates. And now I could author policy based to control the traffic to those VMs. If I go back here and now take a look at my application, I'm going to get told or reported to me this rating service is online. It's a VM. I'm able to get telemetry, metrics, observability information about these VMs now that are being collected by the mesh. Allow me to, let me switch to the last 5 minutes, because that will make the chart look a little prettier. We're able to dig into response time, error rates, even metrics about both of these VMs and how my sidecar is behaving, metrics, information about what API requests or endpoints are being used, just as I would any other cloud native application. And again, just to reiterate, now we have our little lock here. It's talking to it via MTLS, and actually has policy applied to it, because if you recall, we authored that policy previously in that demo where we made sure our front-end application can talk to our booking flow application. Now, our last step in the process, let's say we went through our application modernization, our developers have either carved off some of the portions of the service or totally migrated it to a containerized version of our application. We're able to deploy it into Kubernetes. So now I'm going to deploy the Kubernetes version of my application, my ratings application, into the Kubernetes cluster. And now I really have the most flexibility at my fingertips to control how I start to shift traffic over to this. Now, what I'm going to demos for you is my ratings service. All traffic will still go to these VMs here, unless I can identify it's a specific user. I want to move it to my cloud native application. I could split 1% of my traffic here. I could, since throughout this demo, we've been using 5 different clusters, I could potentially just choose to use the cloud native version in just one of those clusters. Really, the world's my oyster in how I onboard this and shape the traffic and essentially make sure I do a safe, progressive introduction of my cloud native service. So if I refresh my application, it's still functioning. You'll see my logs fly by on my VMs. It's not until I log in as Adam Z that now Adam Z, so I'm inspecting every request and routing it appropriately. If I see the header that my security principal is Adam Z, then it's going to send my request to my cloud native version. I go back to Tetrate, Service Bridge, refresh this one last time. It's now going to tell me my service is running in hybrid mode that has 2 different versions. Takes about 20 seconds for the metrics to actually make it to the back end, get processed and available. So that's why you don't see them quite yet. But it should at least appear in our topology that we now see both versions. And interestingly enough, we're now able to, again, let me look at the last 5 minutes. We're able to look at our services and do some interesting comparisons. So I'm able to actually look at the 2 versions side by side and say, well, did my error rate go up? Is there more latency? Are any of the characteristics of my service, is it performing in a way that would cause me not to want to shift more traffic to it? So it gives me everything at my fingertips that could be needed to progressively roll out this new version of the service. Cool. So with that, let's lastly talk about observability. Going to forego the bulk of these slides and just really quickly show you what additional insights we can get from the platform, because we're running behind on time just a little bit. To go back to kind of
we're not too bad, Adam. So you're fine.
Oh no, we're not. Okay, cool. So to go back to this picture of this management plane, the role of the management plane is to collect and aggregate metrics from all the clusters, all the services that are spread across them, give you a way to make sure your SLOs, look at your SLIs, the indicators that your objectives are being potentially breached, and look across your services that are across all your compute, all your clusters in a single control point. And the role of that management plane is to be the central guy that collects all that. Going back to Zach's original slides, the sidecars themselves, these proxies, are collecting metrics and making them available for something to scrape or collect. And there's some pretty easy ways to do that, contextualized to a single environment. But where it gets hard is not having one single IstioD with a fleet of applications and a couple of sidecars you need to scrape, but potentially n number of clusters and hundreds, if not thousands, of sidecars that need to be scraped, rolled up, and then aggregated together. And so to say it another way, that's where the management plane comes in. A central place that we can ship all these metrics off to give us the types of views that you've seen thus far. As I demonstrated the other aspects and showed you routing and some of the security config, we had been looking at the observability aspects of the product all along. You've noticed we are able to see the metrics about our services, its dependencies. I didn't really go into details in depth, but you can see the color indication, and also the throughput is indicated on these dependency topology graphs. We're able to look across then all of our services and build a service registry that tells us here's all the services and how they're behaving within all my clusters that you own or potentially you consume. Then lastly, easily compare these. So I can very quickly pinpoint, is there a specific cluster? In this illustration here, you see on the right, it could answer my question very easily of, my application is not performing. What is the problem? Well, by looking at this roll-up of the metrics, I can see very clearly, well, this is my GKE East cluster, version 3. Something went wrong there. That guy is nearly 10x, 20x in terms of latency. So that is where I should look to start to inspect and start to triage my issue that I'm experiencing. And then lastly, it allows us to roll up and collect traces. So as we move to cloud native, our services are getting more and more granular. We have more and more dependencies we're consuming over the network. So tracing a call as it spans our microservices becomes extremely important for debugging. And so that's what we'll kind of focus in now on the next bit of the demo here.
Beautiful. There's been a couple different questions. Hopefully we've been answering them around rate limiting and the purpose of the VM gateway. And similar, the VM gateway is really to facilitate both communication for all the services in the cluster between VMs and not just ones you want publicly exposed. It's also, somebody else asked, how does the Envoy sidecar communicate with the Envoy control plane over the VM gateway? So that's the other reason. Anyway, sorry, Adam,
Yep.
please jump back in.
No, excellent point, excellent questions. So as I kind of said through the presentation, we've been seeing these metrics, we've been seeing these things as we've kind of poked around with some of the other constructs of the product. One thing we didn't inspect in depth is the actual service registry that gives us a little bit more of a fine-grained view of all of our services, how they're behaving. I clicked on our review service because that's the most interesting one because it has 3 different versions of it. If I scroll my chart, we can see all my versions across all my clusters. I could potentially graph those, and allows me to drill into the pod level to look at the metrics and look at things like P50 all the way through P99 of its performance. And if I was having issues, I could even see errors that were happening in the sidecar. So though all my requests so far that we've been dealing with have been typically 200s, okay, if I was not getting a non-200 error code and there's issues that the sidecar was detecting, I could actually inspect those error codes and look at what Envoy is telling me about the request, such as I couldn't find a upstream system to connect to service this request, potentially if it's like a 500 error. The one thing we haven't looked at yet, though, is distributed tracing and how we can look at a view of our microservices across a whole bunch of different applications. So we're going to go back to our little helpful service mesh snooper application because we can invoke a request that will traverse the mesh, and I have a couple different services that their role is simply to proxy to another service and eventually land at my backend. So if I refresh this, 10, 20 times, get a little bit of traffic. Now we've created a bunch of service-to-service calls that will be fairly interesting to inspect. And if I narrow down my cluster just to that correct application, so just my demo app, I'll see those proxy services. Looks like metrics have not quite yet flowed in. And always when you're doing it live, 10 seconds seems like an eternity. But we just want to see those metrics from all those. I got logged out. I timed out. Actually, I don't want to be an admin. I want to be this user. Great. Well, hopefully that bought me enough time. So we see all of our metrics coming in from our services, and we should be able to see, at least from a topology view, this call chain. We have our gateway, which hits our front end, which will hit service A, which goes to service B, which goes to service C, which goes to service D, and then finally our backend. So you can kind of see this long chain that's going back and forth. If I scroll to the right, I have an option to trace this. So right now, all my services are good. There's not really anything that would stand out to me as problematic. If there was, I could drill in and see, well, where is my issue happening? But there's no issue right now. So let me execute this little script that all it is going to do is tell a couple of my proxy services to misbehave. So now as I refresh this, we notice it's a little longer. There's some latency interjected. Once in a while, about a third of the time, I'll start to get some errors that get thrown from my service. But this now will make troubleshooting and our call graph and our distributed tracing slightly more interesting for us to look at. So let's brush our metrics here. Now it looks like they all haven't flowed in quite yet. Yeah, well, so we see it in the topology. So if I look at my legend, I now can see, well, my AppDex score is going down. And if I continue to refresh it, it's going to go down and down and down, because this is just the first few metrics that are flowing in. And I could use the metrics that you saw before, those graphs, to start to take a look at, well, I see a spike in requests, but also a corresponding spike in latency, not in that guy, I guess in this one is where the latency should have went up. So our services are starting to misbehave in this case. And here we see the error rates going up. But what we hadn't seen yet is actually how we can use distributed tracing to answer some of the questions of, well, what is going wrong with my service? So they happen to be the most recent requests, but I could search by duration and start to see, well, I have a number of requests that took over 2 seconds, which typically it should have been just a few milliseconds. And also I see a few that are in red, and I could filter just on my error traces. And it now allows me to drill in to see, well, what is going on with my application? Where did my call time break? And here I can pick up two things. First, I can see when I landed on my service B, this guy took 2 seconds to process the request, which is abnormal. It should have been a few milliseconds, but that's not actually what caused the error. If I continue down, I can see, well, finally, when I landed at service C, that service returned a 500 error. And it helps me pinpoint specifically where I should start to troubleshoot in my application, so the app devs can look at the microservice that is going to be misbehaving. Now let's pretend that we've fixed our application. So I'm going to have this little helper app that does a post to some endpoints that now create these guys, set them to behave well. So all my responses come back fairly quickly once again. And so now if I go back and refresh my traces, actually don't see in my last 20 requests, I don't see any errors. I guess maybe they haven't flown into the system quite yet. Let's see. If I sort by time, I don't see anything with drastic latency, so it's a good way to confirm that my system's back in working order. Now my dashboard's given me the last 15 minutes of metrics, so it's going to take a little bit of time for these averages to go down. As I go to like smaller intervals, we'll see these error rates, response times get back to normal. So I believe that kind of concludes the walkthrough of how we can start to put some of both the security building blocks and just general cloud behavior building blocks into our applications. The last bit now is going to be more specific just on Zero Trust, and Zach's going to take us through that bit. Do you want to share your screen, or do you want me to continue stepping through these?
These are only about 6 slides. Why don't you show them for me if you don't mind?
Right.
If you'll just take it full screen for us, yeah. And please, y'all we're going to get into kind of the dedicated Q&A section pretty soon here, as we're coming into the last 25 minutes or so that we have. So please definitely go ahead and start to get any last questions, anything that hasn't been answered or anything in. So what I want to spend the last little bit of time with today is, we've been talking a bunch about the service mesh and different capabilities and a bunch of really cool stuff around kind of stitching it together across your entire infrastructure, across a whole bunch of different clusters and similar. Where I want to end us today is a little bit of framing around zero trust, how I tend to think about it, for us to take into tomorrow, and for us to kind of submit a lot of the stuff that we've talked about today. So first off, when we start to talk about zero trust, there's a lot of vendor FUD. Hopefully, in this call, I think we have a bunch of, well-educated folks who are looking at things like I think it's 800-207, the NIST zero trust paper, and similar, and understand that zero trust is a heck of a lot more than just encryption in transit, right? Even though there's a lot of maybe kind of vendor FUD around in that vein, right? And so when I like to think of it, I like to think of it as centered on 4 pillars. The OMB guide that came out earlier today published, I think, 5 segments that align with this pretty well. So I think this is a pretty decent mental model for you to be equipped with, right? And so when we're talking about zero trust, there's again 4 pillars. So first is the pre-runtime. Before you even get to deploying a binary and running it, there's a whole bunch of stuff that needs to happen, right? What is your process for getting code in, for building that artifact, for scanning it, for doing vulnerability assessment, everything that needs to happen before the deploy, right? That is what, for example, Iron Bank is doing within the context of Platform One. A lot of the CI/CD pipelines that Platform One delivers as well that you can use additionally implement controls and safeguards that are exactly in this kind of pre-runtime zone, right? Of how do I get an artifact? How do I know what's in it? How do I know that it's safe for me to even start to deploy it? Once I have a good artifact that I know I can go run, and when I say artifact here, that can be a container, that's maybe a container plus configuration. But I have this, once I have that unit that I can go and deploy, and I go deploy it, then I need a variety of different runtime security controls, right? Certainly encryption in transit is one of those that I must have. But there's a couple other things that we need as well. And generally speaking, there's 4 at runtime. There's maybe 4 or 5 things that we need to be doing, right? So encryption in transit, right? And that gives us both authentication of what's being sent as well as replay protection. That gives us a whole bunch of different stuff, right? Because TLS is great. But then additionally, there's 4 other things at least that I need to be doing at runtime, which is authentication and authorization of service to service communication. That is authenticating a service identity, a workload identity, and making an authorization decision about that. And additionally, I need to authenticate and authorize some end user credential every hop along the way. And this is a big change, right? In traditional perimeter-based security systems, once you're in, you're good. And we don't tend to, for example, check an end user credential at every hop along the way. That is actually a very important thing, and it's a key tenet of a zero trust system. Because again, the framing question here at the bottom, this is for the first time saying it here, although I think the OMB report earlier today said this almost exactly verbatim, right? Which is the mental framework that you should think about with zero trust is what happens if I expose this workload to the internet, right? What are the checks that I need? And so I need encryption, but I also need, again, that authentication and authorization for every single service of the compute system that's communicating with me and the user of that compute system. Third pillar, I need to be able to understand this continuously, right? It's not good enough to set up and instantiate my platform once and, have a good set of controls once and then let it go run for, a year. That doesn't ground us in a secure stance, Instead, we want to be able to continuously assess the posture and the safety of our deployment of our system and be able to make sure that we're in compliance all the time, right? And we should be able to spot check and reassure ourselves that we are safe and in a good state because of the data coming out of the system. So we need this continuous assertion that the system is in the right state, in the correct state that we configured, based on the telemetry and the runtime data coming out. And then finally, the fourth kind of pillar here is that we need to administer it over top, right? Go ahead to the next slide for me, Adam. So, Platform One is this real life case study of this, right? It's this, we've been talking about it a bunch today. I like the layer cake diagram. This is, ignore the small text in there, it's a little bit too much. But these are, kind of the important pieces that we need to be able to realize the CTA platform, right? There's a baseline compute that you're going to be running on top of. On that, you're going to have an orchestration layer. Big Bang and Platform One use Kubernetes for that layer. Sitting on top of that is a CI/CD system that's responsible for the processes to deploy. Again, this is really, really out of date. So, I think I list in this graphic only 172 approved containers. I think there's like 700 now or something like that, right? So this is an old graphic. After we deploy, again, this is exactly aligning with those four pillars that I told you about, right? After we handle how our artifact gets built and deployed, then we need the runtime security layer, the service mesh layer. This is powered by Istio within Platform One. And then finally, your application sits on top, benefiting from those controls. And sorry, I'm just perusing through the questions real quick to make sure that there's not anything else. And yeah, the OMB released a document today, and I'll link it in just a second. Next slide for me, Adam. Wrong way. Yep. And there's, I think we mentioned previously, there's a bunch of different value streams within Platform One. They roughly align to those pillars that I called out for you, right? The runtime, the pre-runtime, the continuous assessment. And then finally, the administration. And the administration is really what Adam has been demoing all of today using TSP, right? The administration is not something that is kind of packaged into Platform One out of the box because it's a little bit meta, right? It's about how your organization utilizes all of this stuff. But it's very important because that's what gives you the auditability, the safety, and the multi-tenancy that you need to actually use this in a real system, right? For a real organization with many different teams. Next one for me there, Adam. Right, and again, just to come back, the service mesh is really, really bringing us a ton of value in that runtime controls and in giving the baseline data for the continuous assertion of the system state, for being able to understand what our system is doing and that, yes, it is enforcing policy correctly. Next one. And so to summarize some of the key ideas that I want y'all to take home, there's been a lot of different questions today around how we might integrate Envoy with, different risk identification systems, with the different IDS systems, with different authentication or authorization systems. There's been a whole bunch of questions around that that I tried to answer in line as best I could. But the meta, if we take a step back from those individual questions, the key idea that you're all kind of poking around on that's exactly correct is this idea that Envoy is a universal policy enforcement point. And this is why a lot of the folks at NIST, in particular David, who we work with very closely, is so excited about the service mesh, because it gives us this proxy that we can deploy ubiquitously. We can have it next to every application, and we can control them all centrally to have them defer to whatever policy system we need to enforce that policy. And we can do it at L7, right? We can do that understanding the application, not just on like TCP connections, right? So we can actually deeply understand what's going on. This is huge, right? And we would say, if we want to go into the literature, the Envoy forms a reference monitor. And we talk about this in this 800-204B. I'll talk about this a lot more tomorrow in my session. Next slide. So Envoy is deployed all over, everywhere in the entire infrastructure as your policy enforcement point. It's all of those envoys are orchestrated and have their policy managed by the service mesh. Therefore, the service mesh can form our security kernel. This is actually really why some of the folks at NIST are so excited about the service mesh architecture, as the vehicle for starting to secure modern systems, because it lets us realize this 1970s idea that was the root behind the operating system kernel, and somewhere that we know and base our security models on today. It was that idea of the security kernel, a small, focused, concentrated piece of code that is responsible for security on behalf of the system. And in that one location, we can focus our scrutiny, we can focus our audit and security assessments, and really make sure it is safe and secure for us. And then because that's the primitive building block that we're using for the rest of the rest of the system is that much stronger, more secure as a result. So the mesh forms this modern security kernel that we can use to implement policy for the entire mesh. Next one. And then finally, and maybe most importantly, is that the service mesh facilitates cross-cutting change. It makes it very easy to go to one place and change a security policy, an access policy, a traffic management policy, and have that go and be enforced everywhere. And secondly, it makes it really, really easy to start to leverage small, focused teams to take on cross-cutting concerns for the organization. For example, it's really common that we see for folks that are adopting the service mesh, a central security team come on, take over the PKI, the certificate integrations, and mandate encryption in transit across the entire service mesh installation, right? And they can do that with a very small team and enact encryption in transit across the entire infrastructure, right? And manage and maintain that appropriately with, maybe 2 or 3 people for thousands of developers, as opposed to having that burden go out to, every individual application team. And I talk about MTLS, but that's only one vertical, right? So we can start to use Envoy extensibility points to plug in our existing threat detection or abuse detection systems. And we can do that in one place, managed by one team, and all the envoys enforce that policy rather than having every individual team go integrate, right? And so on and so forth for any of these cross-cutting horizontals, right? The service mesh facilitates central teams managing policy for the entire organization. And that really is a superpower. And then next one. And so again, just to summarize, right, the mesh gives us all of these awesome capabilities. Next slide. But critically, it gives it to them consistently across the fleet with centralized control with ease of change. So with that, that's actually the end of our content. We have about 12 minutes left in the session. Certainly, we're about to go into Q&A. I see that there's questions coming in now. We'll start to look at those in just a second. But before I do just want to make sure, please do come join us tomorrow. The full conference will be starting at 11 a.m. Tomorrow, and we're really excited about it. If any of this stuff was interesting to you, but you want to get more depth, you want more insight from some of the folks that have been working on this stuff, please, a lot of them are going to be there tomorrow talking about this in practice, talking about how you can start to apply this and take this. We're really, really excited about it. So please do show up tomorrow as well. Adam, if you go to the next slide, I think we have the full agenda there. And with that, we're going to move over and start to answer questions here that are around. So let me go and we'll pull up here. So the OMB released a document today. Yes, they did. It was pretty exciting. Let me find it for you here, and I will send the link. Let me see. I posted it in the answer to the question around the OMB doc. I don't know if there's an easy way for me to post it in chat for everyone, but maybe I can just present my view real quick, just so we can see that one. I do think this was exciting because it was actually quite validating of a lot of the things that we talked about today. So this again literally came out this morning. If we look at the executive summary here, it's a lot of what we just talked about, right? One of the things that we did not talk about today is person identity or handling end user identity. And that's because in general, the service mesh is plug and play there, right? For you to bring your own system that handles that identity rather than doing it itself. Alrighty, let me see. Let's go through here. Sorry, there's a lot of questions coming in. This is excellent, y'all. We're excited. Yeah, so would you recommend a single control plane across all your clusters and VM workloads, or would a multi-mesh be more appropriate or similar? So one, I hate the vocabulary around this one because I don't like the phrase multi-mesh or similar. So we have a pretty opinionated deployment style. That's based on our experience building reliable systems. So before I worked at Tetrate, I worked in Google Cloud building some of the bigger systems there, including if you've ever gone and used Google Cloud, you've used the resource hierarchy data project creation and the resource hierarchy there. I worked on the identity access management system, some of those large ones, right? And there's a couple of key primitives that you learn for building reliable distributed systems. And one of the big ones is that we want to have local data be local, and we want to have our separate clusters be able to operate independently and without the central coordination. At least in their existing steady state, right? And so that is exactly what we do. And so, in fact, what we do is we deploy a separate Istio control plane instance in every single cluster. VMs talk to a Istio control plane in Kubernetes that is deployed nearby, as in the same AZ, ideally, or in the same data center. And then TSB, or if you're going to try and construct a similar system yourself, your CI/CD system most likely is going to be responsible for publishing the configuration across all of those clusters to enact your mesh behavior globally and not just in one location, right? The problem with running a single Istio control plane across all of your clusters is you have a single shared failure domain. That Istio control plane dies, all your clusters are down, rather than like if it dies in one cluster, that one cluster is down. So you don't have very many axes to be able to do reliable and safe operations if you only have one Istio control plane. And so that's why we avoid that. According to Zero Trust, never trust, always verify. How does this fit in with the service mesh across clusters? Please give a complete example. So hopefully, you've seen some of this, right? So first off, the communication that we're doing even across clusters is encrypted with MTLS. And again, it's not just that it's MTLS. It's not just that there's encryption in transit, but the certificates that we use for that encryption in transit encode an identity. And we can authenticate the identity in that certificate to have an authenticated principal to be able to apply policy on. That's what Spiffy, the spec, gives us. And so with that in hand, now I can do an authentication and I have an authenticated identity. Therefore, I can do an authorization decision on every single request from that client, right? So that's how we always verify. We're not trusting, we're always verifying. Every single request that's coming through, we are performing authentication and authorization of that request to assert that, yes, it is allowed, right? So hopefully that answers that question. And I do just want to add that we can do the same for end user credentials attached to that request as well. Is there a better way to incorporate VMs into the mesh? This is a first class way of bringing them into the mesh, right? It's not really, I'm not sure if you see the, it looks a little bit like a bolt-on. The reason it looks like that is because there's not tight integrations with, unlike for Kubernetes, right, where there's tight integrations with service discovery. Unfortunately, there's a ton of different VM runtimes that exist out in the world. And so there's a long tail of service discovery integration that would need to happen in Istio upstream to be able to use all of those, right? And so certainly that's happening. We've done things around EC2, for example, in this vein and all to make them more and more first class. That is a long tail of work that is ongoing. What's the difference between the infrastructure layer, the platform layer? Doesn't the cloud provider host some of this stuff? And the answer is yes, right? I think we answered at least part of this, hopefully in text, but the Kubernetes is part of your, usually is consumed as part of the cloud provider, but it is, higher level software, right? So we can consume parts of the stack from cloud providers, parts that you do yourself, but we can still have a consistent, coherent platform that is Zero Trust and the Big Bang deployment and all of that, and its guides and all of the stuff that Platform One has produced account for that and discuss it. The recording, the slides will all be shared. I'm just reading through, trying to see. Hopefully, folks have the OMB document link now. We're just going through. There's quite a few questions coming in, so we're going through them.
Hey, Zach, I think the one that just came in from KP is super interesting about that comment to treat everything as exposed to the internet. And then just turn that on. That's not what we're saying, but you almost have to assume that that's happened with your infrastructure. If you're assuming you don't have a compromise, you're probably fooling yourself. So it's a way to help you prepare for that.
Yeah, like don't misunderstand, right? So assume that it's, imagine it's exposed to the internet, assume it's exposed to the internet because your network is compromised somewhere, right? So somebody does have access. That does not mean that you necessarily should go open it up to the internet, right? The point is to be in a security posture such that that's not something that would be ridiculous for you to do if you had to, right? But just because you have this new set of tools doesn't necessarily mean that you need to abandon your old tools entirely either, right? The reason that we would say, for example, abandon some of the old tools is because they're too brittle to be able to achieve the things that you need to be able to do, right? So, for example, as long as your DMZ is not ossified and slowing down the ability for your developers to deliver value, keep the perimeter, right? And don't expose everything to the internet if you don't need to, right? And you'll be safer overall because you have more layers, right? Defense in depth, right? But no matter how many firewalls you have, no matter what your DMZ is, assume that there is a compromise somewhere in your network and that people can an attacker can use that. That's what the Zero Trust model stipulates. And so an easy way to put yourself in that mindset is assume that my service is exposed to the internet. So that's why we say that as kind of a shorthand. So hopefully that helps kind of answer that a little bit. Awesome. I think that's all the questions that we had. We have maybe just 1 or 2 minutes left for any last minute questions. Otherwise, thank you all. This has been really, really excellent. Again, we have the full conference that's starting at 11 a.m. 11 a.m. EST, 8 a.m. PST tomorrow. So please join us. There will be quite a few different folks that will be talking. We're pretty excited about it. And you'll get a lot more of this stuff in maybe not quite as much depth as this. You'll get a lot more kind of a broader overview. And then secondly, we will be sending out a sign-up link as well for folks that are interested in going through a lot of this hands-on. Again, I know that quite a few folks had asked. Because of the number of attendees, we were not able to do this interactive hands-on like we would have liked. We will be holding very many smaller follow-on sessions where we'll be hands-on and you can actually go and do this in Kubernetes clusters that you bring. And so that'll be happening soon. With that said, thank you all. This has been excellent. Oh, one other interesting question in the last minute. How is TSB not a single point of failure? Great question. The answer is that we've built the entire system to be highly resilient, right? And so at each layer in our infrastructure, there are caching points and similar that are going to hold on to the configurations around. So basically any part of the tree can fail and the rest of the infrastructure is going to continue operating in its last known good behavior, right? The whole point is to avoid spots, single points of failure in the system. Alrighty, and with that, I think we'll tie it up.
Yep, thanks a lot, everyone.
Yep, thank you, everybody. This has been great. We look forward to seeing you tomorrow. Michaela, if you're still on the call, is there anything that you would like to close out with before we go?